Okay, let's remind ourselves where we left off. A little bit of a cliffhanger before we left, because we had just introduced delta G, but we hadn't seen what an amazing character it would turn out to be. So before break, we said delta G is this thing, and delta G tells us if a reaction wants to go forward or reverse. It tells us if a reaction is thermodynamically favorable or unfavorable. So the key point that I repeated on 2 slides right before we left was if delta G is positive, then the reaction wants to go in reverse. If delta G is negative, the reaction wants to go forward. In other words, the reaction wants to go to lower G, lower Gibbs free energy. So whichever side has lower Gibbs free energy, that's the place the reaction is going to want to go. And I said it on 2 slides in a row. There are a number of different ways you'll hear delta G talked about, and one of them is the idea that delta G is a measure of the usable energy from a reaction, or the amount of useful work that you can do using the reaction. And so I want to talk a little bit about that interpretation. We're going to come back and look at different ways we can interpret delta G at different points in the lecture. But if we think of it as a measure of usable energy, our definition of delta G was delta G equals delta H minus T delta S. And what is it that H stands for? Let's remind ourselves. H equals what? Enthalpy, which we said for our purposes sort of means what? Well, the total energy, but for us, the changes in H are going to be changes in which kind of energy? Heat, all right? It'll be heat given off or heat absorbed. And it's because of a change in potential energy of all the attractions and repulsions. So that's what H stood for. What did S stand for? S was, well, H was entropy. So S was entropy. Entropy is what? Disorder. Or dispersal, how spread out things are, how chaotic they are. All right. So if we look at delta G as this combination of delta H and delta S, the delta H part here is really the change in potential energy, or the change in potential energy of all the attractions and stuff. This is how much heat that the reaction can give off. Give off if it's negative, absorb if it's positive. And that's due to particles attracting each other. And so you might think, well, if the reaction gives off a certain amount of heat, well, great, that's all good. All of that energy can be used. But the thing is, it can't. There's a cost. Oops. The delta S part is really, this is the change in disorder. That whole T delta S part, that's how much entropy takes a toll on how much useful work you can do with a reaction. So for instance, if delta S is a positive number, that'll actually increase the amount of energy you can use. But if delta S is a negative number, if you have a reaction that makes things more organized or more ordered, less disordered, then this minus T delta S term is like the cost of organizing things. So you want to build something. Part of the energy that you put in is going to just go into lifting the pieces and moving the pieces into the right places. Part of the energy that you put in goes into making it organized. And so that T delta S term as a whole really is the cost of organization. All right, that sounds kind of abstract. So we're going to look at a bunch of examples and see how this applies to actual reactions. So on the next 4 slides, you've got 4 different chemical or physical processes. And for each one, I want you to decide whether you think delta H is positive or negative, and whether you think delta S is positive or negative. So this is a good review. You can talk to each other, get back in the idea of what delta H and delta S are. So for the next 4 slides, I want you to take some time. You don't have to do the delta G part, but decide, do I think delta H is positive or negative, and why? Do I think delta S is positive or negative, and why? And then as a group together, we'll talk about what the implications are for delta G and what our conclusion is. Okay? So take some time. All right, for this first one, Kyle, at your table, what did you guys say for delta H? All right, so delta H would be a negative number. Delta S would be a positive number. All right. So, what's the reasoning there, Molly?
Well, I thought that it would be H would be less than 0 because we talked about how it's
Yeah, this is combustion. And what's the one thing you know always happens during a combustion reaction? Energy is released. It gives off heat. Right? Fire is hot. So it makes sense that delta H would be negative. It's releasing heat. All right, then delta S is positive. What's the reasoning behind delta S being positive? More moles of gas. Over here we have 17 gas particles. Over here we had 13.5 gas particles. Anytime you're taking some big molecule and breaking it into smaller molecules, it's a good bet that delta S is going to be positive. This is making more disorder. All right, so then we have delta G. Well, that equals delta H minus T delta S. T is temperature, and it's temperature on the Kelvin scale. So T is always going to be a positive number. So if we look in delta H is a negative number, and delta S is a positive number, then as a whole, minus T delta S becomes a negative number. So this whole thing is negative. So we have a negative number plus another negative number. So delta S is always going to be, delta G is always going to be a negative number. At any temperature. So this is a reaction that pretty much always favors the reverse. Always favors the forward direction. This is always thermodynamically favorable. As we talked about before break, it's kind of a good thing, though, for us that combustion reactions have a very high activation energy, which slows them down and prevents them from just happening all the time, because we wouldn't be able to really exist if everything was constantly burning. So they're always thermodynamically favorable. They may not be happening, even when you have the reactants together, because they might not have the activation energy. What questions do you have from that example? The question is the enthalpy always the opposite of the entropy? And the answer is no. I gave you 4 examples here, so I gave you every possible scenario. So, second example. Well, who recognizes this equation? It's like the reverse of a combustion. It's photosynthesis, specifically. So this is basically the equation for photosynthesis. All right. So for this reaction, what's your guess for delta H? Daniel? Delta H is positive. Yeah. Yeah, it's the reverse of a combustion, so the reverse of a combustion isn't going to happen on its own, so energy has to be put in. Yep. So delta H is a positive number. If we went through and calculated all the bond energies here, we would see that the bonds in the products are weaker than the bonds in the reactants. Going back to the previous reaction, if we looked at all the bond energies here, we would find the bonds in the products are much stronger than the bonds in the reactants. Specifically, if you just look at in C8H18, that's all carbon-carbon and carbon-hydrogen bonds, those bond energies are much lower than carbon-oxygen and hydrogen-oxygen bonds. So in other words, the bonds in the products for this combustion reaction are much stronger than the bonds in the reactants. For this reaction, the bonds in the products are much weaker than the bonds in the reactants. Right, so delta H is a positive number. How about delta S? Oh, we already heard from that table. Augustine, what did you guys say for delta S for this reaction? Said delta S was negative. Why? Yeah, there are fewer gas particles on the right. We're taking these 12 molecules and turning them into one big molecule plus 6 small molecules. So definitely decreasing disorder. So if we think about delta G being delta H minus T delta S, this is going to be now a positive number minus a negative number. So when we have a positive number minus a negative number, this is going to be a positive number. So for this reaction, is this ever going to be spontaneous, or is this ever going to be thermodynamically favorable? No. So how do plants make it happen? They use the sun, right? You need a source of energy. A term that we don't often use in chemistry, but if you took AP Bio, you used all the time, would have been reactions being endergonic versus exergonic. That refers to the sign of delta G. So this would be an endergonic reaction. Energy goes in. So you need a source of energy. For plants, that's going to be energy coming from the sun. So they use the sunlight to force this reaction to happen. Any questions there? All right. Going back to our interpretation of delta G from this in this way, if you think about photosynthesis, if you think about this reaction, it takes a certain amount of energy. Delta H is the amount of energy it takes just to rearrange the bonds and trade in the strong bonds for weaker ones. So delta H here is the cost of changing stronger bonds into weaker bonds. And then this reaction has a second cost, and that's the cost of organizing things in a specific way. Because when you take these 12 molecules and make this one big molecule, and then you have the 6 oxygen molecules coming out, you're organizing those smaller molecules into a bigger one. And so this delta S really is the cost of organizing. So a reaction like this with a positive delta H and a negative delta S is a huge energy cost, because you have to pay to do both of those things, to put in energy to do both. Whereas the prior one, where delta H was negative and delta S was positive, there you were releasing energy by trading in the weaker bonds for stronger bonds. So this is like the energy you get out by changing weaker bonds into stronger ones. And delta S is the energy you get out by allowing the things to become more disordered. So by allowing them to follow their natural tendency to become more disordered. So that's the way we can interpret this delta G as the amount of usable energy from a reaction. Is that each of these components, enthalpy and entropy, they each have their cost or their benefit depending on which direction they go. All right, next example, for those of you at home, make sure you add in this CO2 that I put in red because it was missing from the notes. All right, this is a reaction we actually did in the lab. Does anyone remember doing this in the lab? Sean, how do we make this reaction happen in the lab? We heated it up. So we put in heat to make this happen. So what do you think that means about delta H? Positive. Delta H is positive. If you have to put in heat to make it happen, that means it absorbs heat. And usually when you're taking particles that are bonded together and separating them into different particles, usually that involves, not always, but usually that involves a positive delta H. But we know delta H is positive because we had to heat this up to make it happen. All right, how about delta S in this case? Paulina, what did you guys say for that? Delta S is positive. Why? Yeah. Solid turns into gas. So greater disorder afterwards. So now we have delta G equals delta H, which is a positive number, minus T times delta S, which is a positive number. When I take a positive number minus a positive number, is the result positive or negative? We don't know. It depends. Depends on which positive number is bigger. All right. So what does that mean? Well, remember this is delta H minus T delta S. Delta H and delta S are roughly fixed numbers. They might vary a little bit, but they're roughly fixed numbers for the reaction. So what's the main variable here? T. So the size of T is going to matter. Let's say T is 0 or very close to 0. Which term in this equation becomes the most important term, delta H or delta S, if T is really small? Delta H is more important when T is small, because if T is really small, the second term becomes negligible. As T gets bigger, if T is really big, now the second term, minus T delta S, becomes bigger and delta H becomes less significant. So at low temperatures, delta H is going to dominate, and at higher temperatures, delta S is going to dominate. So let's think about this. Which one of these is making the reaction favorable? And I'm going to go back to this statement that I outlined last time. Chemical or physical processes are driven by a decrease in enthalpy or an increase in entropy, or both. So for this reaction, do we have a decrease in enthalpy or a decrease or an increase in entropy, or both? Which do we have? We have an increase in entropy. So the increase in entropy is what's telling this reaction to go. Meanwhile, we have delta H telling the reaction, no, don't go. Right? These two things are giving opposite messages in this case. Delta H is saying, don't go. Don't happen. Meanwhile, delta S is saying, go for it. And the thing is, as T gets bigger, whose voice gets louder? Entropy's voice gets louder at higher temperature. So this gets louder and louder. As the temperature increases, because that second term becomes more important. So this is a reaction that at low temperature won't be favorable. At low temperature, delta H is winning. But you raise the temperature, and it'll happen. Eventually, it'll reach a point where it does become thermodynamically favorable. So in this case, the reaction is not favorable below a certain temp, and then it'll be favorable above a certain temp. So there's going to be some temperature threshold where this goes from being unfavorable to favorable. Notice on our first two reactions, the two voices were saying the same thing. In the first reaction, both voices were saying, go for it, yeah, great reaction. In the second case, both voices were saying, whoa, no, no, this is bad, don't, no way. But here we had conflicting voices. So the question is, what happens if delta G is really close to 0? Well, then the reaction will not have a huge driving force. So we will come back and talk about interpret delta G in a different way later on. Delta G, another way to look at it is delta G tells you how far a reaction is from equilibrium. So if delta G is a really big negative number, that means the reaction is really far from equilibrium and it needs to go a long way in the forward direction to get there. If delta G is a big positive number, we said that means the reaction needs to go in reverse. So if it's a big positive number, that means it's way far away from equilibrium and it needs to go way in reverse to get to equilibrium. If delta G is a small number, it just means it's close to equilibrium already and doesn't have far to go to get there. Yeah, and that'll also mean, you know, there's not much energy left that you can get out of that reaction. So an example of something where delta G is a small number would be a dead battery. It's a battery where the reaction has come close enough to equilibrium where there's not that much driving force to make it happen anymore, and so it can't operate your cell phone or your computer or whatever anymore. All right, so last example. I'm guessing by process of elimination you could already figure out what delta H and delta S are for this last one. So we've done negative delta H, positive delta S. We've done positive delta H, negative delta S. We've done both positive. And now this last one, both are negative. Yeah, delta H is less than 0. Delta S is less than 0. All right, how do I know delta H? If I didn't do this by process of elimination, how would I know delta H is less than 0? It's condensation, which means we're bringing together attracted particles. From the beginning of the year, we said when you bring together things that are attracted to each other, you lower their potential energy. So you allow those gas particles to condense. They're going to release energy because they're going to run towards each other. Yay, I missed you so much. And then why is delta S negative? Yeah, it's hard to phrase because you have more, is it becoming more ordered or less disordered? Well, they're both the same thing. So it's becoming more ordered or less disordered. Two different ways to say the same thing, although less disordered seems weird because it's a double negative. Well, that's what entropy does to us. Right, it's going from a gas, which is all spread out, to a liquid, which is condensed. So now our two voices, delta H is saying, go for it. Right? Decrease in enthalpy. That says, come on, reaction, you can do it. Or in this case, not reaction, but condensation. And then delta S is saying, whoa, no thank you. So delta G is now a negative number minus a negative number. So again, we don't know what it is until we know the temperature. So at low temperatures, whose voice is more important? H. So at low temperatures, this reaction will be favorable. At high temperatures, it won't be favorable. And that corresponds with our experience. At high temperatures, water tends to evaporate. At low temperatures, water tends to condense back to a liquid. So this is not favorable. Oh, sorry. Favorable at lower temperatures, not favorable at higher temperatures. What questions do you have from those 4 examples, which covered all the bases? So this all boils down to this pretty elegant statement, I think. The chemical or physical processes are driven by a decrease in enthalpy or an increase in entropy or both. You should be able to look at any reaction and make some guess or estimate as to whether enthalpy is increasing or decreasing, whether entropy is increasing or decreasing, and then draw some sort of conclusion about whether that reaction wants to happen or not. Doesn't anyone want to say, like, wow, this is cool. The universe totally makes sense to me now, and my life will never be the same? Well, someday. This is your first introduction. I got to say, this is a topic that I took for the first time. I took chemistry, like 20 years ago. And I've been teaching it for 15 years. And every year I sort of understand it a little better. So I don't expect you to completely comprehend all of thermodynamics at this point. But hopefully we're planting some seeds. And over time, I hope you come to appreciate just the power of this idea that it really tells us when things are going to happen and when they're not. And you can look at the whole world through that lens. So I think we're going to call it a day there because what's coming up is really getting into the numbers. All right, how do we do calculations with this stuff? And it becomes more tedious. Less big idea, more, okay, now I have to look up these values and look up those values and crunch some numbers. So that's what we'll be doing next time. And then we will kind of return to the big ideas at the end and relate delta G to equilibrium and just what is the relationship between delta G and the equilibrium constant, that kind of thing. All right.